Global shipping moves the overwhelming majority of world trade, and it operates almost entirely on petroleum fuels. The International Maritime Organization has set a strict regulatory course, requiring international shipping to reach net zero greenhouse gas emissions by around 2050. With the IMO's 2025 committee decisions mapping a clear path toward pricing carbon emissions, operators are forced to find viable, large-scale alternatives today. This regulatory pressure has elevated a very specific candidate molecule, ammonia. Its primary appeal rests on a single chemical fact. Ammonia contains exactly 0 carbon atoms. Run it through an engine, and there is absolutely no carbon dioxide released from the combustion of the fuel itself. It is a surprising pivot for a chemical historically engineered exclusively as an agricultural fertilizer feedstock, which is now being re-engineered into a heavy-duty marine power source. Engineers are not forcing this molecule into the marine supply chain out of convenience. They are doing it because strict regulations and basic chemistry demand it. Utilizing ammonia introduces an immediate engineering paradox. The exact absence of carbon that makes the fuel appealing to regulators makes it highly resistant to combustion. Thermodynamically, it is an unforgiving fuel. Ammonia has an exceptionally high ignition temperature and a very low flame speed. It also operates within a remarkably narrow flammable range. Compared to standard marine diesel or natural gas, ammonia is reluctant to ignite and extremely slow to burn. Beyond the combustion chamber, ammonia presents a severe spatial constraint, measured by energy density. Ammonia carries roughly 1/3 the energy per unit volume compared to standard marine gas oil. This has a direct consequence on vessel architecture. To achieve the exact same operational range, a ship requires 3 times the tank volume, forcing architects to trade away valuable cargo space. Selecting ammonia means marine operators are intentionally accepting extreme volumetric penalties and severe combustion resistance strictly to eliminate carbon dioxide at the tailpipe. Before the fuel ever reaches the cylinder, engineers must design around an immediate hazard. Ammonia is highly toxic to both ship crews and marine life. Occupational exposure limits are extremely stringent, with danger thresholds sitting in the low tens of parts per million. Acute physical irritation to human operators occurs at concentrations well below the volumes that matter for actual engine combustion. This toxicity dictates the entire design and operational philosophy of the fuel delivery system. The safety architecture begins at the port, requiring highly controlled shore and ship-to-ship bunkering procedures. Inside the ship, the primary mechanical defense mechanism is containment. Engineers utilize double-walled fuel piping throughout the vessel. Alongside physical barriers, the system requires continuous active gas detection and high-capacity ventilation systems along every single segment of the fuel supply skid. The physical reality of an ammonia-powered ship requires an engine room completely redesigned with toxicity containment as its primary operational directive. To actually burn the fuel, the dominant mechanical solution engineered for deep-sea marine applications is the dual-fuel compression-ignition 2-stroke engine. Engineers overcome ammonia's low flame speed by forcing the liquid into the engine cylinder through extreme high-pressure injection. A heavy ammonia fuel rail and a specialized fuel valve unit work in tandem to maintain and deliver this immense pressure directly to the injectors. But pressure alone is not enough. The critical workaround required to guarantee ignition is the introduction of a conventional pilot fuel. A small dose of conventional diesel or fuel oil, roughly 5% of the total energy output at full load, is injected alongside the ammonia. This pilot fuel ignites first, creating the intense thermal environment required to force the combustion-resistant ammonia charge to burn fully. This specific architecture provides a massive fail-safe advantage. The engine retains complete fuel flexibility. If an ammonia bunkering network is sparse or the fuel supply is entirely unavailable, the vessel can immediately fall back to running on conventional marine oil. This dual-fuel approach is the vital bridge technology. It guarantees operational reliability today while setting the mechanical foundation for a carbon-free future. This architecture has moved past laboratory theory. These engines are entering commercial service now. In July 2025, Swiss engine designer WinGD delivered and installed its X52DFA engine, built under license by HD Hyundai's engine business in South Korea. The installation targeted a 46,000 cubic meter LPG and ammonia carrier constructed for the maritime operator Exmar. This delivery marked the first ammonia-fueled two-stroke marine engine successfully brought to market. Market adoption is accelerating, with an early order book of around 30 of these ammonia engines spread across bulk carriers, container ships, and gas carriers. The heavy engineering phase of engine design is largely complete. Carbon-free deep-sea combustion is a deployable physical reality. Analyzing the post-combustion exhaust profile reveals a sobering reality. Removing carbon dioxide introduces a complex new suite of nitrogen-related concerns. The first major byproduct is nitrogen oxides, or NOx. This forms because both the ammonia fuel and the intake air contain nitrogen, which bond together in the intense heat of the combustion chamber. Encouragingly, full-scale test data from 2025 shows that NOx runs 40 to 50% lower in ammonia mode than in standard diesel mode on the exact same engines. Despite this reduction, a selective catalytic reduction system, or SCR, is still required in the exhaust stream to meet strict IMO Tier 3 emissions limits. The second, far more dangerous byproduct is nitrous oxide, or N2O. This is a greenhouse gas roughly 270 times as potent as carbon dioxide over a century. If N2O escapes the stack unmanaged, it will completely erase the climate benefits of switching to a carbon-free fuel. Engine makers have successfully mitigated this risk, holding N2O to safe, low single-digit parts per million levels during testing. The final variable is ammonia slip, the highly toxic escape of unburned fuel leaving the engine. Testing has consistently kept this well below the strict 10 parts per million safety threshold. Ammonia's emissions profile is tractable through advanced combustion control and SCR aftertreatment, but it conclusively proves that carbon-free does not automatically mean clean. Ultimately, the true climate benefit of this engine technology depends entirely on the well-to-wake life cycle calculation of how the ammonia is manufactured. Conventional, fossil-derived gray ammonia offers little environmental advantage. The entire model relies on green ammonia, produced by using renewable electrolysis to split water for hydrogen and combining it with atmospheric nitrogen. Utilizing green ammonia can yield a well-to-wake greenhouse gas reduction of up to 90% compared to conventional fuels. But this introduces the final binding economic constraint. Green ammonia is currently vastly more expensive and far scarcer than its fossil-derived counterpart. Marine engineers have successfully solved the mechanical complexities of the engine itself. The ultimate pace of global decarbonization now rests on building the infrastructure to supply affordable green fuel. To review the detailed mechanical specifications of these dual-fuel architectures and access our continuing education modules, visit ProReadyEngineer.com.